Greetings, everyone. At long last, this is the lecture you've been waiting for, where I'll introduce you to some of the basics of threads. It's one of my favorite topics because there's some myths that need to be busted. I guess we should change the title of this one to Threads and Fasteners. We're going to start our discussion of fasteners today. All right, so first things first, there's a little terminology. Admittedly, a little awkward terminology, but we'll run through it. So here's a bunch of things that all look primarily the same, right? Especially these two things here. So these things are really the same part, right? But depending on how they're used, they get a different name. So when it's done like this, it's this thing is threaded into this base material, threads here, right? Then we call it a screw, right? When it screws into some base metal. Whenever it goes through, so these two are clearance holes here. So those are clearance holes. There's no threads in there. Then we call this thing a bolt, right? But if there's no threads in there, something has to hold it together. So that's the nut, right? So exact same part. One is a screw. One is so this one is a screw because it threads into here. This one is a bolt because it works with a nut on the other side of it. Okay. Now there's another one that looks a lot like that, and that would be a stud, right? And the way a stud works is it threads into something on one end, and then it has a nut that holds it down on the other. So it's very similar to a screw, except that it's got an independent nut on the top here, right? So here's the nut, and then threaded holes. Threaded hole, right? And then finally the simplest one is a threaded rod and nuts, where the whole thing is threaded. There's nothing permanently attached to it, both clearance holes, and I'm making gestures here that you guys can't see. So there's both clearance holes here, there's clearance holes here, and then there's a nut on both ends. So that's a stud and a nut. All right, so that's basically how the fasteners work. Now let's look at So my goal here is to teach you guys primarily about fasteners, right? But before we do that, we're going to look at power screws and threads, because I think this leads to a nice understanding, right? So we have this thing here, which is some sort of a screw jack, and this is pretty typical of how a screw jack looks. Well, maybe not. Maybe this is more. Whoops. Oh boy, what happened there? There we go. This is probably a typical screw jack here. And so we call this is a screw jack, right? And a lot of times, like on older cars and whatnot, it would come with a jack that looks a lot like this. So we can turn the black part, all right? So this part turns, and it goes around and around, and then it lifts the weight up like this, right? Similarly, we could take this one here, where again the dark shaded part turns. This turns, and then same deal, it goes up. So somehow we have to have we call this thing here a collar, right? Obviously, my car, this is my car or my boat or a trailer or whatever I have to lift. The load frame, for instance, in the 307 lab. This thing is not moving. This thing is not moving, but this does, right? So that means we have to eliminate some friction with some sort of that's a collar there. We have to eliminate friction there. We have to eliminate friction there somehow, right? And so basically what this thing allows me to do, it converts rotational power work to vertical work. or power if we divide it by time. So that's a quick overview there. We're going to look most closely at this one, where if I said I apply some force here, I cause this thing to rotate, and I want to lift this weight. All right, that's kind of be the goal of the next few slides. All right, first a little terminology though, or more terminology. So the pitch, right? The pitch of threads is right here, and that's the distance from the peak of one thread to the peak of the next thread, right? But typically, we don't talk about pitch. We frequently refer to the threads per inch, and I'll talk about that in a sec. And then we have the major diameter, right? And this is the major diameter here. And that is what's the biggest diameter of this whole fastener, right? So when we talk about bolts or machine screws, right? If there's one that comes to mind, the classic ubiquitous 1/4-20 screw or bolt, right? The quarter this is a 1/4 inch, and that is let's do that in blue. That's the major diameter, and then the 20 is the threads per inch, right? So typically with English or ISO or American nuts and bolts, we refer to them as their major diameter and then their threads per inch. All right. Minor diameter, on the other hand, is down here. So this is the diameter. That's the smallest at the deepest point in the threads. What is the diameter there? All right. So from there to there is the minor diameter, and then we have what's called the pitch diameter, and the pitch diameter goes right in here. That's kind of between the top of the thread and the bottom of the thread. Okay. Alternatively, you could say that's where the major and minor diameters, or it's between the major and minor diameters where it goes gap, thread, gap, thread, gap, gap, thread, gap, thread, and the gaps in the threads are the same width. There's also an internal thread angle. We'll talk about that in a little bit. All right, so some more terminology as we prepare for our static analysis of these things. We have, so basically what this is, it's an inclined plane wrapped around some sort of a cylinder, right? So pitch, we already talked about 1 over threads per inch. So this would be the 1/4-20 or 3/8 16. And let's see, there's 4, number 440, right? Those are really little bitty ones for assembling little electronic parts or whatever. These numbers here are all, oops, I don't want to do that. I want to do this. This is the size, and this is threads per inch, that should be a 16. Let's erase that. Not 3/8, 1/16. It should be 3/8, 16. And then these guys here, diameters, size, and then threads per inch. All right. Now, what is the lead? The lead is the distance that it travels with 1 full revolution. And so you may look at this and say, wait a minute. Here's the lead. Here's the pitch. Why do we have 2 different terms for that? And I'll talk about that in a sec. The lead angle is kind of like if you thought about this, if you turn this on its side, you said I'm trying to climb a mountain or climb a spiral staircase or something like that. What is the angle, right? How far above horizontal am I going? The mean diameter of the thread contact, the mean diameter. So we have, I want this. I want to go like that and then like this. The pitch diameter here, right, is this line, right? Well, we can also call that the mean diameter, and that's the same thing. That's just this diameter between the tip of the thread and the root. Now, threaded fasteners come in, or threads in general, come in a different way. Two different flavors as far as the handedness. Right-handed threads. So if they're right-handed, let's make a quick note of this. Right-handed threads. So clockwise to tighten, and then counterclockwise to loosen. Some people say righty-tighty, lefty-loosey. I personally can't stand that. Let's just call it clockwise and counterclockwise. And then left-hand threads are the opposite of that. Oh, and there's also single, double, and triple threads, right? Most of the fasteners that we're used to dealing with have a single thread, right? But some might have what's called a double thread, where there's actually two helixes going around, around the cylinder, right? And so in this case, the lead is, whoops, go back to this. In this case, the lead is twice what the pitch is, right? Because if I just go from thread tip to thread tip, that's the pitch, but if one full revolution goes the full lead, right? So that's a subtle difference there. All right, now let's go back to this topic of the power screws, a screw jack. So jacks, load frames, worm drives, some hydraulic presses maybe, all work with power screws, right? These are the most common here, right? Are the Acme threads. For instance, if you looked at the MTS load frame, right? Those are the 10,000 computer-controlled ones in the 307 lab. Right, those, if you look inside and see how those work, right, they work with Acme threads, whereas the older 60,000 pound machine where we did the compression test and whatnot, old 60 kip machine has square threads on it, right? And then there's modified square threads where there's a very small angle, modified square threads here. So it looks mostly square, but it's got a small angle. We have Acme stub, here. So one thing to note here is that there's this angle alpha, right? And alpha is really, let's zoom in here a little bit. So this is, why does it keep going to pen? Eraser. So this is 1 alpha. This angle in here is 1 alpha, right? So that means the angle between here is 2 alpha. That's just, oftentimes threads are given by 2 alpha. I don't really know why. That's just kind of how it is. All right, so I think that's enough on the terminology there. So now we have to look at the inclined plane analogy, right? I'm ultimately trying to figure out how hard do I have to push here? How hard to push, alternatively, or the torque, right? In order to lift this weight, right? Ultimately I want to lift my car there, by moving this up, and I want to know what that has to be there. All right. So I kind of take this thing here, and I unwrap that, and then I'm going to be pushing, this block up this hill, like Sisyphus, right? Except I have to, because I'm going to be applying a horizontal force, right? So this force here is horizontal, right? So I have a horizontal force that I put on this little block, right? And then the normal force, right, that's pushing up on it is actually somewhat inclined here. And then I've got some frictional force that's also tipped a little bit. But my weight is straight down. All right, so these are straight down, vert, and this is horizontal, and these two are both tipped. Right, so we're going to have to account for that, right? But it gets worse if we go back and said, this would be square threads here. Gesture, right? So square threads here, but in reality, most of the time we're using Acme threads like that. So I've got to go take a closer look at how this stuff works here. And there we have to consider the double incline plane, right? What is this all about? Well, the sum of the horizontal forces is 0. We know that from statics. So I've got to take my Q, right, which is just straight up a horizontal force. But then my horizontal force here, right, is the frictional force, so N times F, times the cosine of the lead angle, right, times the cosine of lambda. Furthermore, there's another horizontal force, and that's in the sideways direction, and that's due to the tip of the threads. So that comes from this here, right? Similarly, I could do the same thing in the vertical direction here, and so I know the weight, which is straight up and down, but then I don't get all of it, right? My normal force doesn't count completely to lift this thing, so that's why I have to consider the sine of lambda, and then the cosines deal with kind of my radial direction here. So let me, that's a good way to say it, actually. I'll try that. So these deal with vertical forces, vertical in radial direction. All right. Okay, so now what do I know? I know my weight. I know my angle. I know my other angle. Friction, I don't know. We'll talk about that in a little bit. We're not sure what the friction is. If we go back here a few slides, we remembered. We had this collar. This collar here, gesture. So I want that collar there to reduce some friction. Got some ball bearings down there to reduce some friction, right? But typically you don't see the friction here very much. So do we have friction there? I don't know. We'll have to talk about that. Okay, so anyway, back to the static analysis here. So if I want to know how much torque I need, right, for the differential element. I just had the little bitty force I had to push on my one little block just to raise that little W. And it turns out to be a function of all this other stuff, right? But to raise the entire load, W, how much torque do I need total? Well, I have to lift the entire weight, and then I have to have some big force, right? But this is a horizontal force, right? I'm not so interested in the horizontal force. Ultimately, I want to convert to torque. So I need to convert this thing to a torque. What is torque? It's force times distance. So torque equals the force times the distance, right? Force times distance gives me a torque. And I discovered that that's kind of the inverse of what I had. And so I get it to be a function of the friction and the angle and the angle. I know all this stuff. I know that angle. I'm not sure about that friction. I'm not sure about that. Right, but there's two extra sets of friction if I'm doing a torque balance on this thing. I have, this is the torque for lifting, right, this part right here. That's for lifting, and then this is just a frictional loss, right? And, in reality, there's going to be some friction at the collar, right? Where did that happen again? Where's the collar friction here? Yeah, so the collar here, right, we got to remember this. There's some collar friction. So I really need to account for that when I'm trying to figure out how much torque or power I need to lift a load. All right, so just be aware that we know the things that we know. I'll put in green here. Let's see if I can do that. So I know that, 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 right? But some of my unknowns that I'm going to be a little unsure is the friction there and the friction there. So the friction, this is between the threads. So the threads, and this is for the collar. All right, there's two frictions I don't know. All right. So back to threaded fasteners, right? That's the threads in fasteners are typically very standard, right? Standards are important. There's the Unified National Coarse and Unified National Fine threads. These are probably the two most common ones you'll see at the hardware store. So, for instance, this would be the ubiquitous quarter 20, and then the fine version of the same thing would be quarter 28, right? How do I know that? Just a lot of time in the hardware store buying stuff. And then the ISO threads are typically metric. And they actually give, it'd be like 6 millimeter by 1 millimeter, right? Where this is actually the pitch, and this is threads per inch, TPI. All right. Now, we haven't seen a table yet, so it's about time we see a table. Here we go. This is the quarter, right? This is the major diameter, and we know the basic major diameter is a quarter an inch. We typically see for a UNC screw 20, right? Now the basic pitch diameter, remember the basic pitch diameter is, how far is it to this point here, right? To that kind of center line of the threads. And so we can go through and find that that's there. We know the actual sizes, I'm going to skip those two here. The lead angle, that's kind of important for calculating torque stuff, is degrees and minutes. One really important thing that we need to know, and we're going to get into this more when we do analysis, is the tensile stress area. And so if I go all the way across here, right, so that's the effective area for sigma equals load over area. Okay, it's not actually a quarter inch, so we calculate that area based on a diameter that's somewhere between, we can't use this area because that would be too big. We can't use that area, so that would be too small. So we're going to use something in here. So somewhere in there. Oop. Somewhere around here to get the tensile stress area. All right, so what are those stresses, right? There's two kinds of stresses. Well, actually, kind of four kinds of stresses that show up. The first one is really easy, torsion, right? We know how they do that, 16t over pi d cubed, old news there. So that's kind of the classic torsional stress. So here we need what is the axial stress on this thing, and to do that we take the load over the area, but this of course has to be the tensile area. All right, and then we have bearing stresses in threads and the shear stresses of the threads. We'll talk about those next. The bearing stresses at the threads are the compression or the contact stress. So really we should call this a contact stress. But it's not like a cylinder in a cylinder or a ball in a plane. It's just the contact stress right here. Right, so that's the bearing stress. Wow, did that go wrong? So we'll call that the bearing stress. And it's I'll talk about that later. And then the thread shear is this load right here. That goes to there. That's the shear load across the base of the thread. And then there's just a little bit of geometry that goes into that, right? And then we have to look at these lines of force that are kind of like these guys that are going like that. If we consider this metal a spring, and after mechanics materials and after all the work we've done earlier this semester, we can kind of think of this material as a spring. Whoops. So which one of these springs is the longest, right? This is all steel. So here's the first thread in our bolt, and then here's some load acting on it. So this is all steel. This is a relatively short kind of line of force that travels along here. Here's a little bit longer one, and here's a little bit longer one. So my question to you, we have, let's call this, so we consider these, how about we'll call these fibers, right? I'll call this, let's zoom in on this a little bit. This is fiber 1. This is, because it's the fiber that goes through the first thread. We'll call this fiber 2, and we'll call this fiber 3, right? And if we do that, I wonder, which fiber carries the most load. Right? Well, the shortest one does, right? So the longer the fibers get, i.e. the farther I get away, the more threads are engaged, the more stretchy each one of these fibers becomes. So the result of this is that 90% of the load, because of the stiffness of these different fibers that we're loading, carried by first three threads. Right, and that's one of the big takeaways from the class, I think, that you only need to get 3 or 4 of these things engaged, and then you can pretty much carry the full load of the bolt, right? And so that's what I think is so cool about this kind of stuff, is that the geometry of the threads, let's go back to gestures here, this dimension of the threads, this dimension of the threads for the contact stress, the bearing stress, the shear stress at the threads, and then the overall axial stress on the threads. The bolts and nuts and threaded rods and stuff like that are so carefully designed that nothing's overbuilt, right? The threads, the shear, the bearing stresses, the torsional stresses, and the axial stresses. Let's make a note of this. These are all geometry chosen. So the safety factors, same for all 4 stresses. That was terrible handwriting. Sorry about that. So the geometry, so we don't want the threads to be stronger than the bolt. I gotta keep, we don't want the threads to be stronger than the bolt. We don't want them to be stronger in contact than they are in shear, right? So that's why all these are so standardized, right? Okay, finally, we got to look at, oops, get out of there. What would I do? Help. I want to go back to this one here. All right. So, yeah, this is, here we go. Preloading, right? This is, what most of us would call tightening the bolt, right? Right. And that is, you tighten this thing to get some initial tensile force, right? And that is nearly equal to the proof load, right? And the proof load or the proof strength is the load or stress that does not cause measurable permanent deformation, right? And for different classes of fasteners, that strength is different, that load is different. So in general, you want your initial load to be the strength times the area, right? So this is, so that's in megapascals, and that's in millimeters squared. And so that means this whole thing here becomes something that's in newtons. and then we take some fraction of that, right? And typically we want to go up to about 90% of the proof strength or the proof load for that particular bolt. All right. Now I just wanted to make note of this here. This is right out of the text, right? So it says blah 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 blah. An initial tensile force is nearly equal to the quote proof load in quotes, which is defined as the maximum tensile force that is not blah 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 blah, right? And it says, so the initial tension, we just talked about this, is some fraction of the proof load for the bolt, where it's, SP is the proof strength of the material, right? Holy cow, what a mess. And typically it's around 0.9 like this. So, and this is in quotes because it's all a little bit wishy-washy, right? Here's a picture of the yield point, right? And remember how we define the yield point? There's some offset here from 307 is so much work. So 0.2% offset. So if we took this all the way to yielding, right, there's some plastic deformation. Whereas the proof load is no perceptible plastic deformation. So what they do is that they'll load this up to about 90% of its yield strength, hold it for 10 minutes, and then release it. And then they measure it again. And if it's still the same length, right, they can't tell that it's any longer, then we say, okay, that's a safe proof load. So that's how they do that. This is kind of confusing, but for the most part, we're going to look at proof loads. All right. So measuring the preload, right? When you first tighten this, right? So how much do you tighten this, right? Well, if I said, hey, assemble this thing, put the cylinder heads on the engine block, or get the tension your spokes on a bicycle. What is something else you have to tighten? Just tighten anything. How much you tighten it, right? How do you tell someone how tight to make something? Pause. Yeah, right. You're going to say, well, I'm going to apply some torque, right? Well, sure you do. Because just like we did before, when we said, so lift a heavy load, right? We calculated some torque that we need to do that. Well, if I just want to get some initial tension, I can just set my load equal to the initial tension, right? And for this diameter, we use the major diameter of our fastener. Well, then we need to know, so this friction coefficient was a big deal. So this is friction of the thread, metal on thread. And then this friction is the head of bolt or nut on base metal, right? Because we can't really put bearings in. We can't really put bearings into here to reduce that, and we certainly can't put bearings on the threads. So we've got two frictions that we have there. So if we assume that the coefficient of friction here is, let's call this steel on steel. And then we consider this as pretty typical, 4 degrees. Right, we discover that the torque necessary is about 0.2 times the preload times the diameter, right? Does this work out? Yeah, so this is, the force here is in newtons and the diameter is in millimeters. So that would give us Newton millimeters here, right? However, big unknowns though, right? These are really big unknowns, such that, I'm going to make that even a little bit bigger. This is only good to plus or minus 30%, right? Huge unknowns there. Why are there these huge unknowns? Friction is uncertain. So a torque wrench is simply not the best way to do this. It's the easiest, it's the fastest, right? Every spring I take the winter tires off, and every winter I put the snow tires back on. What do? I use a torque wrench, right? But in the back of my mind, I know that this is only good to plus or minus 30%. All right, well, is there a better way to do it than to use a torque wrench? Well, now we have to dig a little bit deeper. So here I've got two plates held together by a bolt, right? Is this a bolt? Yeah, it's a bolt. So this is a bolt here because it goes through some clearance holes. And then here's a nut that's on the bottom side to hold this thing all together. I know that, well, I'm going to look at this as two parallel springs, right? I'm going to take these two metal plates, and those are going to get compressed a little bit. And then, so this, I'm going to treat this as one spring. And then I've got some bolt that's going to get stretched, right? As I tighten this thing, the bolt is going to stretch a little bit. So I say that's in tension, right? So the clamping force, let's call this the clamping, and this is the bolt, that equals the initial. Right, so I've got the clamping force, the bolt force, and that's going to be equal to the initial tension, right? If we treat this as springs, right, this has got the clamping force is the stiffness, right? So this has some Kc over here, so that's stiffness times the elongation, right? So whatever the elongation is of so this is delta B here, or delta, shoot, erase that. So that's delta C, right? How much do I squish that thing? And then this is delta bolt for how much does that stretch, right? But I know those two have to be equal because it's in static equilibrium. So the total, the total elongation of this whole thing is down here. Total elongation is the, how much does the clamping stuff get compressed plus how long does the bolt stretch, right? And then the two things together, right, that total elongation has to be this force times some combined stiffness. And so this is combined stiffness of bolt plate system. Right? And just like resistors, the reciprocals add up. All right. So what I can do, if I know I want a certain number, a certain initial tension, if I know what I want this to be, and then I just need to I can relate very easily the total elongation to this if I know the stiffnesses, right? And so if I want a certain initial tension, and I know the stiffness, I know how long I have to move it, right? And how many times I move it is related to, how far I move it is related to the lead and the number of turns, right? And so this leads us to the technique, which we call the turn of the nut method, which is much better. So a lot of times, if you see really good instruction manuals, they'll say hand tighten. So example, the instructions, the specifications will always say hand tighten plus, that's supposed to be a plus 1/4 turn, or hand tighten plus 1/2 a turn, or hand tighten plus 3/16 of a turn, or whatever, right? And so that's a much better way. This is much more accurate. Okay. So torque wrenches are fine, they're quick, they're easy, less accurate than the turn of the nut method. All right, well, how do we get these stiffnesses, right? This is the last thing, and these lectures always get longer than I intend them to be. But I know that for the bolt is really easy, right? The bolt stiffness is just AE over G, right? Bigger, if I have a bigger diameter, right, it's going to make it stiffer. If I have a stiffer material, it gets stiffer. But G is the effective length of the bolt. That's also called, why is it called G? It's because it's the grip length. Right, the grip length is how much is in here. Oop, I didn't want that. I want this. Okay. Now it's a little trickier here because I can't simply say, the area of the bolt, this is easy. Right, the area of the clamped members, that's a little tougher. How do we get that? Well, if I consider this to be kind of a frustum, like this, and a frustum is a cone with one of it lopped off like that, that's kind of a frustum. I can, just do a little geometry here. I can take, the average. So basically this is the average of outer cylinder. So I could draw, and let's do that in a different color. Maybe blue, I guess. So here's an outer cylinder. Right, like that. So that's the outer cylinder. And then combine that with an inner cylinder, which is this guy here. So that's the inner cylinder. I'm going to get rid of that because that just made a mess. So let's try that again. The outer cylinder is if this whole thing got compressed, which I know it doesn't. And then the inner cylinder, I'll put that kind of dotted. That would be this inner cylinder here. Right, so the effective cross-sectional area really is the average of the inner. The outer cylinder, well, that whole thing doesn't get compressed. The inner cylinder, more than that gets compressed. And I take the average of those two, and I get this. And of course the whole, right, that doesn't do anything for me, so I have to take all that area out. All right. There's other ways to do this. Along formulas, you can integrate, the deformation within there and all that stuff. But really, this is much, so we're going to call this oversimplified. Oversimplified, but close enough. Okay, so that's how we can get the stiffnesses of those two things. All right, well, we're almost there. Hang on. What if I had, well, let's say I bolted the bolt a cover onto a pressure vessel of some sort. Right, and I've got some really spongy gasket in here. Super spongy. Spongy? Yeah, whatever. Okay. And I can bolt this thing to some initial tension, right? So the bolt has some initial tension in it like this, and whatever that initial tension is going to be equal to the tension or the compression that's on my gasket. The problem is, as if I lift on this, holy cow, I can't spell today either, apparently. So if I lift this by some delta, right? If I lift that by some delta, the compressive force, right? Compressive force goes down by the stiffness of the clamped members, so that's Kc times delta, right? But Kc is really, really small. Right, so my clamping force doesn't really drop at all, right? Okay, I gotta slide this, that doesn't work. Let me erase that, I got too far to the edge of the tablet here. Barely changes. Right, the clamping force barely changes, but this, so this force increases by delta times the stiffness of the bolt, and that's really big, right? So the more I stretch this, so in this case, the bolt takes all the load. Right? Because I have to stretch this bolt by some amount delta, right? And it's very, very stiff, so the load in the bolt goes up very quickly. And I have to, decompress that gasket by some delta, right? But since there's hardly any stiffness to this spongy gasket, right, that stays just about level, right? That's kind of one extreme. Next extreme is, what if I have a really stretchy bolt, and it's just metal on metal here. So that's metal on metal, and this is super stretchy, so it's like rubber. Now, if I apply some delta to this, right? So if I displace the lid by delta, right, what happens, right? Bolt increases, or F sub bolt increases, right, by delta times the stiffness of the bolt, but the stiffness of the bolt is just rubber, right? So that's effectively zero, right? So it doesn't increase at all. Whereas the clamp, F sub plate, we'll call that the clamping force, decreases by that same delta times the stiffness of the clamped members, right? The clamping stiffness, which is big, huge, right? So we see the same thing, or kind of the opposite thing happen. The bolt tension doesn't increase at all because it's got such a small stiffness, right? Whereas the clamping force drops significantly because metal on metal has a very, very high stiffness. And so what happens down here, so here's where, get my pen to work. Lid comes off. And then we get a leak. There, all right? So that's what happens there. Now, in reality, steel plates and steel bolt, typically, the clamped members, so these are the plates, are about 4 times as stiff as the bolt, right? Approximately. So that's ish. Right? Why is that? Because if we go back here, right, this area is pretty big. This area is pretty small, right? So a lot of area right? A pretty small area. So if we have a lot of area here, right, that's going to be stiffer than the little bit of area there. All right. So what happens is, how much does the bolt pick up? Right. So this is the bolt will wind up as I apply an external load. I'm going to just do this. As I apply this external load this way, right, and that's the force in the bolt will increase some, right, but not too much, because its fraction of the stiffness, this is the bolt's fraction of total stiffness, right, that's this, right, is relatively small. So this picks up, so bolt picks up about 1/4 of load, right. This is the plate's fraction, right, which is considerably more, right. So the plates, let's call that, lose about 3/4 of the load. So that's the subtle relationship between. So as I stress a clamp, a clamped joint, the bolt picks up some of the force, right? And the plates get reduced, but the clamping pressure gets reduced, right? So that's what allows me, the fact that the bolt doesn't pick up that much of it, allows me to go back here and say I can preload a bolt by quite a bit. I can get it really close to yielding, right? And as long as the bolt is pretty stretchy relative to the plates, I'm not in too much of a danger of damaging or yielding the bolt, right? So I think that's a pretty neat relationship between how these springs and fasteners and different materials work together. All right, so to put this in terms of equations, this is exactly, so this picture really is the same as this. So the clamping force, so the pressure between, or say that's the force between, so this is the force within plates, within or between plates, is this compressive load here. That's the initial load, right, whatever it is, minus the plate's share. So it's minus the plate's share of the external load I apply, right? Whereas similarly, the force in the bolt here, right, is the initial tension plus the bolt's share of the external load, right? So the compressive force gets reduced by the plate's share, the bolt gets increased by its share, and together those two add up, right, to this is the full external load. So this is the full external load here. And that's it. A little longer than I thought. Hopefully not too confusing. Office hours. Please